Welcome to another video. This time I want to look at reference counting optimizations. So my programming language Plum uses reference counting for garbage collection, which means that, let's say you have some variable a that is 5. That means that somewhere in memory a 5 exists. And every value that exists has a reference count. So for the 5, for example, we store there's one reference to that, the a variable. And when you use the value, for example, by assigning that to another variable or putting that into a list, putting that into something else, then we just increment the reference count here. Meaning that in that case, we would store 2 in here. And whenever a reference to a variable goes out of scope, for example, if a function returns, then all the local variables that were defined within the function, they go out of scope. And all referenced values, we decrement the reference count by 1. Which means that we can just track if the reference count reaches 0. When that happens, we free the memory for that value. That is enough to collect all garbage, because in Plum there are no cycles between values, because you can never mutate values, you can only create new values. So you can basically store all values on kind of like a timeline, and they can only reference previously created objects. So yeah, there can be no cycles, because that would require 2 objects to point to each other, which would mean one object points to another object that is created later. Having this like purely immutable mathematical feel in the language means that a lot of values or objects actually get created. For example, in most languages like Dart, Java, Rust, and so on, for a list you usually have a push or append function that just appends another element to the list. And the way that works is that it grows the list on demand, but usually it just puts an element somewhere in the memory, like at the end of the list. In this case, however, the append function actually takes a list and an item, and it returns you a new list that has this one item added. That sounds inefficient, and it is by default. So I have a plan on how to do some optimizations there that also include reference counting. Because we can not only use reference counting for tracking which values are no longer in use and can be freed, but we can also use reference counting for opportunistic mutation. Meaning that when we see that the reference count of some value is 1, and we want to like push something to a list, for example, then we don't actually need to create an entirely new list, but we can just change the list in place, just add the element there at the end. And that's basically what I want to enable today. Not exactly that mutation, but the groundwork for that. And that is smarter reference counting operations. So what are like reference counting operations? Basically, in the compiler, when you write code, for example, create some list. Let's actually write that down. A variable a equals list, or some function make list. Make list. Sorry for the horrible handwriting. And then you map that list to something else. For example, you might increment. Let's say that there's a list of integers. You might want to add 1 to every integer. So you would do something like call the map function, with some closure that increments every element, and then you might want to filter the list to some elements, and so on. And basically this original list currently is kept around until the end of the function. So let's say this entire thing is inside some function, and I'm to too lazy to think of a name, this a variable here is basically kept around until the end of the functions. So, you know, let's actually write down what the function does. So let's say that the map function takes a and then some closure that I'm not going to write down. And down here we have some filter function that takes b and some closure, and then c is also returned from the function. At this point, where c is returned, this is where all variables go out of scope. So a is kind of removed, the object, the original list is freed. But also, b is also freed at this point. And c is also freed at this point. No, hang on, c is actually returned, so it's not, the memory of that is not freed. And one way to think about that is with ownership. So you can think of it like every function and every operation kind of takes ownership of some values, and it provides you ownership of some other values. For example, the make list function, it just returns your list. It gives you ownership of the list. You are responsible for decrementing the reference count of that list. And when you then pass that a to the map function, you need to provide ownership to the map function, which means at this point in the code, before calling the map function, you kind of need to increment the reference count. Yeah, let me maybe have a clear, visual, semantic thing. You know, here we get ownership of that a. Here we put ownership in there, and that means we need to, well, kind of duplicate ownership in between there. And same for the b. For the b, we want to, the b variable is here. In the end, it goes out of scope. And at this point, we need to dupe the b variable because we also want to pass that into the filter function. And the filter function provides us with a c that we return here. So that kind of goes, out of scope. Yeah, that's one way to look at how kind of values flow through your program. And you might think that is inefficient, and it is, because we don't really need to increment the reference count here, because a is only used for this map function, never, nowhere else in this entire function. That means that we don't even need to keep around the original list until the end of this function. We can just kind of give the map function complete ownership of the list. If we don't duplicate the reference count, if we, initially the reference count is 1, if we don't set that to 2 in here, but instead we leave that as 1 and we just pass ownership directly into the map function like this, then the reference count is 1, and that means the map function can maybe optimize stuff. It may, for example, free the original list while it's iterating over it. If it's a linked list, that works. And while it's creating the new list that it's going to return. And that means that the memory of those lists kind of get reused. The old list gets deconstructed as the new list gets constructed. So we kind of have this intermingling of deallocating memory, freeing memory and allocating memory. So that's what I want to do today. Kind of change the reference counting behavior from one where variables are freed at the end of functions to one where they are freed as early as possible, and where we just give them to other functions if that works out. So I want to end up with something like this. All right. That's the rough plan. So let's dive into the compiler. Let me quickly like set up stuff in here. Okay, so the compiler is organized into stages like most compilers, and the ones relevant to this video are the yogurt and the pudding. Yogurt stands for your official graph using resolved types. It's just a representation of the program where every expression has types, and expressions are decomposed into these simple, very simple expressions like calls and stuff like that, rather than having nested expressions. So the order of operations is defined at this point. And that yogurt gets converted into the pudding, which is the program using dupe and drop instructions to neutralize garbage. So this is where we add these reference counting operations. And this is apparently what's not. Well, it is working, but it is not optimal. So let's look at a simple program. For example, this one. Here we have the main function, and it just takes the number 2. This dot syntax means that it calls the star function that takes 2 integers with the 1 on the left here, the 2 and the 1. And that is the result. After that, it calls the plus function with that plus 4. I can also like organize that into something that looks more like Lisp, just something like this. Yeah. So first we kind of multiply 2 and 1, and then we add this thing and 4. This kind of prefix notation of operations. Let's compile that. And I enabled debug printing of the yogurt and pudding, so we can see how those look. Yeah. Most of the time spent compiling the compiler. All right, this is done. So this is the yogurt, the representation of the program. And you can see that in here we have nested expressions. We have this addition of a multiplication of numbers. Here that is all decomposed. First we create the value 2. That's an integer. That is this temporary variable 1. Then we have this value 1, temporary variable at 2. And then we call this, workspace from the standard library, the int multiply function that takes 2 integers with these 2 temporary variables. And then we create a 4 and do the same with the plus function and return the 5 at the end. Yeah, that seems reasonable, I hope. Right, so what I want to do today is change how that is mapped to the pudding. And the pudding looks like this. And you might see that this is not optimal. So here we create a 2, and then we create the 1. And then because we call this multiply function, hang on, before getting onto this, let's just say, for each of these original kind of expressions that we have, in the pudding, we actually drop all of them at the end. So here we have a function, and all these temporary expressions, these temporary variables that we've created, all of them get dropped here. And then every time we use one of these, we dupe that. So here, for example, we want to pass 1 and 2 to the multiply function. And the multiply function will receive these as arguments, like our main function does with some value. We can even look at that. Yeah, it receives these as arguments, and it's going to drop them at the end. So we need to increment the reference count of these arguments before passing them to this function. That's what we do here. Dupe operation increments the reference count by 1, and the drop operation decrements it by 1 and frees the value if it's 0, and then drops the children. Right. Yeah, so we did this. Here happens the same for the plus function, and in the end we dupe the expression that we want to return, so that when we drop that down here, we don't actually free the memory. Yeah, that is not efficient. Like you can see that this dupe and drop, for example, they cancel each other out. We should just remove all of that. And even here, like duping 1 and 2, just so that we can drop them down here. We can remove all of that. We can just create a 2 and a 1 and just call this multiply function, which takes care of dropping them, freeing the memory. And then we, call the multiply function, we call the plus function with the result and the for, and we don't need to have a single drop instruction in this entire function if that works out correctly. Yeah, and that's basically the insight, that most code that you write is actually kind of, you have complicated expressions that are nested, like here, for example, or like here. Sometimes you declare variables explicitly and you can use them multiple times, but most of your usage of values is going to have this linear feeling that every value is created once and it's used exactly once as an argument to something else. And that's why, doing this, like spending some time to do something more clever than this, I think is worth it. Okay, and before we dive into the code, I also want to make some things clear. First of all, this is kind of a semantic level. Later in the compiler, we'll see that we don't actually dupe and drop values, at least for these kind of primitive types. We only reference count values that actually require memory allocations, such as linked lists or other recursive enums. For simple integers, just storing the reference count is that takes more memory than just copying the integer when you call some function. So under the hood, not every, at this compiler stage, it makes sense to treat every value as being reference counted, and that makes things a lot more simple and a lot more uniform. But I just want to mention that later on in the compiler, some of these actually get optimized even further on a more fundamental level, so that we don't actually need to reference count all of these values. Okay, yeah, that's the first thing. And the second thing I wanted to mention is that, that this is not like my original idea, but instead there's this paper called Perseus, a garbage-free reference counting, with reuse. And what they do is they kind of describe that approach. Oh, I'm just seeing I can't. I'm in front of the paper. Well, anyways, they use reference counting for garbage collection, and they also use that reference count for reusing memory when possible. And they kind of describe this approach of bringing ownership onto the function. That's this part right here. If you have some reference, then ownership of that reference is passed down into each function. The map function in the example, mapping a list of numbers. The map function is in charge of freeing the original x's and y's. And I want to do something similar. Basically, every function is responsible of freeing its arguments, and hopefully that's gonna work out nice. All right, let's maybe, should I draw something? I don't know. Another thing I wanted to mention is that this is not only good because of mutation, but it's also, this is especially good because it interleaves allocating new memory and freeing old memory. And that means that not only is your peak memory usage reduced of the program, which is nice, I guess, but the program will also run much faster because of memory locality, because that old memory is still in the cache, and that everything is still densely packed together instead of allocating entirely new data structures somewhere else in memory and then no longer using the original ones, freeing them. Okay. Right. So that being said, actually, I think yeah, I'm going to describe the general approach I want to take, and that is to go through the code in reverse, I think. Because rather than going from beginning to end and being like, oh, here's a call that uses the 1 and the 2, these two expressions, so we should dupe them. What we want to do is, if the 1 is no longer used anywhere else in this function, then we don't want to emit this dupe instruction, but instead we just want to pass ownership of that value immediately to the multiply function. And to do that, it's useful to know which expressions will be used later on. And down here, it is also useful to know which expressions will have been dropped before. So I think it makes sense to actually go through the code in reverse, through this code right here. So basically, we would look at the 5. We would say, okay, 5 is supposed to be returned. So 5 should still exist down here. And then we just walk up this code. No, 5 should exist. So here we call some other function plus with 3 and 4. So we know that 3 and 4 should exist, and 5, we don't need to care about that because it's defined here. Yeah, so basically, after we've kind of compiled this, when we see this call, walking through this function in reverse, we can see that 3 and 4 are no longer, like, we haven't even met them, but we know that this is the last usage of them because we haven't, we know that we need 5 later on, but we don't know anything about 3 and 4, which means that this is the last time that they are used. Which means we don't need to emit these dupe and drop instructions before this addition. We know at this point that we can just take 3 and 4 and that's it. Yeah, here we see the 4, and we don't need to do anything about that. Here we see the 3, and we see that this requires 1 and 2, which means that because we don't know 1 and 2 anymore, like we haven't seen them down here, that means that we don't need to dupe them before calling this function. Yeah, because we know that this is the last usage of these expressions. Yeah, things will get tricky when we have like the control flow splitting at some point, and we have a switch, and then with multiple branches, we'll figure that out. All right. Yeah, let me maybe show you the definitions of these compiler stages. Yeah, the yogurt is not super surprising. We have a bunch of functions. Every function has a DAG, a directed acyclic graph of expressions, and a yogurt body. The yogurt body takes parameters, has children, and returns an expression. And these IDs, they refer to expressions that are stored in this DAG. Yeah, and yeah, these are yogurt expressions that each contain this operation and a type, and the operation can be any of these. You're creating an integer, creating a string, putting things into a struct, accessing a field of a struct, creating an enum, switching on a value, creating a lambda, calling something, creating a first class type, which is weird. We'll get to that. Yeah, and these are not really contained in the body of functions. All right, and yeah, the pudding looks pretty similar, to be honest. The only difference being that there's also dupe and drop down here. Oh, and apparently some got simpler. Like this is something I haven't seen in the yogurt. And it doesn't use a DAG, but instead it has this list of all expressions. And it has, oh yeah, not just general IDs, but pudding IDs, which index into this list, which, yeah. There was a bit more boilerplate here. Anyways, the important thing is these drop and drop expressions and how to add them. That happens in this stage right here, which is not super long. You know, it's like 150 lines. And basically everything I'm going to do in this video is just, oops, wrong one. I wanted to move myself. Everything I'm going to do in this video is just editing this file here. Nothing else. Alright, let's maybe go through that. So, converting a yogurt expression to pudding. Well, for these primitive expressions like ints and strings and also types, yeah, they just push an expression and that's it. We don't need to care about reference counts. You know, in this case, for example, creating the int 2 in here just becomes creating the int 2 in the pudding. The interesting parts are expressions that reference other expressions, such as structs. For structs, we iterate over the fields, and then we emit this dupe operation to increment the reference count of that field, because by putting that into the struct, there's now an extra reference that points to that value. And then we actually push the struct instruction, or operation, expression, whatever. Yeah, member gets the member of a struct. That is not entirely correct what we do here, actually. Yeah, well, we'll need to see what we do there. Yeah, for enums, duping the enum payload, they can have payloads. For the switch, we get the condition, we dupe the condition, and yeah, we compile the switch cases. For lambdas, we dupe the captured variables and then just push a lambda. For calls, we dupe the arguments and then push a call. Yeah, which can either be a lambda call or a call instruction, or an instruction call. Yeah. Anyways, yeah, that's basically it. We also have other stuff like converting a body. That's actually interesting. Converting a body to pudding means, well, we have this builder with parameters. We compile all of the individual expressions, and then in the end, we push a dupe instruction for the expression that we want to return. And then we drop all the parameters and the expressions defined within this function. That's basically it. All right. So now we want to go through that function in reverse, basically. But you know, it is pretty late, so I'm not going to do that today. Yeah, sometimes else. I'm here with some nice tea, so I think we can get started. Actually, the first thing I want to do is refactor some things, because the previous compiler stages before the pudding, aka egg and yogurt, they use a new data structure, the DAG, which is a generic type representing direct acyclic graphs, rather than having these kind of ad hoc definitions within each module. For example, the pudding fun right here has a list of pudding expressions that it owns, but then the actual content of that, the pudding bodies, they just have IDs, which are indices into this slice, which is kind of weird. So right now I'm just going to change that from to a DAG of pudding expressions. It captures some IDs, and the body, we don't no longer have pudding IDs, but instead we just use the generic IDs. Yeah, the pudding body has params, expressions, and IDs. Yeah, pudding operations and plum types, that is still fine, I think. Alright. Yeah. And then next up, I would maybe change this. So the pudding fun builder, instead of that, will just pass around a DAG directly. Boom. And the body builder, we don't really need that, I think. I mean, yeah, I guess it doesn't hurt to create that. Putting body builder is just that. Body builder with these doesn't have a parent. Yeah, on the pudding fun builder. Actually, I think it makes sense if it has a parent, which is just the DAG. Yeah, let's maybe name that DAG, and then that should work. So it has a mutable reference to the DAG of pudding expressions. Sure. Yeah, rather than calling that parent, we just have a DAG of pudding expressions, and we put that parent down here as well. That still fits on the same line. We can, yeah, there is a put function on the DAG, so we don't need this anymore. For pudding body builder, this still makes sense because we can just do parent builder.dag.put, that thing that returns us an ID, and then we push that to our parameters. That makes sense. Yeah, pushing an expression also puts an expression into the DAG and then adds that to our list. Yeah, this is just on the DAG that already exists. On the body builder, we just do builder.dag.get. Yeah. Returns on a body builder. Oh, I see. It's like the finish thing. Let's call it finish. That's fine. This, we don't really need that, I think. Nope. Just create a pudding fun directly. Yeah, this finishing a pudding body builder with an ID returns a pudding body with the params, the expressions, and the returns ID. And let's maybe call that returns. That's a bit more descriptive, you know? Okay, yeah, getting something from a pudding fun return. I mean, sure. Return type. Yeah, this is, we use the generic one from the DAG. You see, it's like a lot of these simple things, they get a bit easier. Okay, and then you're converting something to pudding, and converting pudding to the next stage is we're gonna have to adjust that. First, that yogurt to pudding thing, where we don't really have a fun builder here, we just have a DAG. And we have a body builder, we have a mapping, which will just be from ID to ID, I guess, yeah. Okay, and this just creates new stuff. Hang on, it literally just returns a pudding expression. Okay. Sure. Yeah, and this is what we'll adjust. Okay. Yeah, converting a body. Doesn't have a fun builder in here, it just has a DAG. Yeah, I think that is fair. And in here we just have a body builder of that DAG. And then we use that body builder. Yeah, something like that. That is called finish. With the return expression, the fun builder is just gonna be a DAG of pudding expressions. The mapping is gonna be a mapping from IDs to IDs. Yeah, the captures thing is, let's call it DAG. Doesn't really have finish. Instead, we'll just return the pudding fun with the captures and the DAG, the captures, and the body. You see, that is pretty nice. Okay, and I think this can also be simplified just like that. Now, let's see if that works. Yeah, let me get a terminal up and running. Yeah. Okay, so the next compiler stage, converting the pudding to something else. There, our pudding ID no longer exists, that's just the ID. But apart from that, I don't... Oh, okay, but apparently something... Oh yeah, this is in the something to pudding stuff. We do some sort of create. We should instead do a put. And the DAG is defined in here. Okay, yeah. Sure. Fun builder. Nope, that's just the DAG. Does that fit on the same line? It does. Clean. Even simpler. Yeah, 72. And the pudding directory. Yeah, there's just that. I cannot even remove this, and instead, encourage people to use the DAG directly. Yeah, so this would be in the in the pudding. Yeah, use the DAG directly. Where are we now? In pudding Presto. Okay, we're slowly going to the next compiler stage, fixing the errors here, and then we'll at least have done something already. 467, 467. Indeed. Well, this is kind of meh. Okay. Yeah, get pudding fun ID 49494. There's probably some places where we don't even need to pass down the entire function, but the DAG would be enough. But yeah. 504, we're making progress. We are making progress. Well, 457. And 363. So why did I do that again? I mean, it could just as easily have said just have a fun to get. Would have been fine. Well, too late. How it works. Okay. Yeah, that's kind of the pre-work, you know, and cleaning some stuff up. And that's actually stuff. Oh yeah, I did this before the video, basically commenting out the printing except the pesto and waffle. And this is now changed so that it uses the DAG. Here's the DAG and the pudding. And now comes the interesting part. Now we want to go through the function from bottom to top. So when converting a function, yeah, we're looking at the parameter types. Oh, hang on, we're in the wrong one. Something to put in here. Yeah, this is not a long file. You know, it's like 150 lines. And this is the interesting part. When converting a body to pudding, what we do is, rather than iterating through the parameters and the IDs and stuff like that, we instead go from the bottom to the top. So I'm not sure how. We need to maintain some sort of mapping, maybe? No, needed later on. This will just be a set of IDs, which yogurt IDs are needed later on. Not the pudding, but the yogurt IDs. Yeah, so we create a body builder that is fair. And now I'm just gonna flip these parts in the in this function basically. This right here, we don't do that. We don't just drop all expressions at the end, the parameters and IDs, or the return value. Instead, we start with the return value. And we say, well, needed later on, we need the return value. Boom. And then when we compile those other expressions, when we encounter that return expression, we know for certain that this will not be freed. The others will be freed by default. They will be dropped. That's the idea. And this will also flip that around. So we'll first go over the children, then the parameters. So this is exactly the wrong way. First looking at the return expression, then at the children, then at the parameters. And even for these, we should iterate on them in reverse. I think there's an iterref function. I'm not entirely sure. Please exist. Nope. ref iter maybe. Otherwise I'll just look in the standard library and see what's in there. Oh, this seems to work. Okay. Oh man, so we have some sort of ID. So the first, well, we're basically building the function from the bottom to the top. So yeah, the return value we'll put that in here in the end. That makes sense. But for all expressions, we basically want to push and build the code for building the expression. And this code right here comes afterwards in the actual body. And then we want to immediately drop the expression unless it's needed later on. That's the key thing. So if needed later on, if oh hang on, if not needed later on but contains ID, then we'll immediately drop the expression. So we'll do some of what I removed down there. And you maybe retrieve that from here. Yeah, something like this. Then we'll just drop the... Oh, yeah, we don't really have... we don't really have the ID yet for that expression, because we haven't compiled that yet. Well, that is kind of meh. I'm gonna add a to-do in there, but that is weird. Okay, and that evaluates to something, to the ID, I guess, but we'll just ignore that because it's just a drop instruction. Yeah. So because we're building the body from the bottom to the top, we first have this drop, and then the actual code for, you know, putting the expression in there. fun.dag.get ID to pudding. Okay. So, I guess what I want to do is, yeah, we have this mapping, but in front of that expression, oh yeah, we will also need to insert dupe instructions for those that are also needed later on. So I'll just pass this in there. And these drop. Yeah, so this is just similar to this one. If the param is not needed later on somewhere in the body, then we will immediately drop the parameter. Okay, and then there's toPudding function that also needs to accept this. That does not seem right. That should come like that. Is a similar concept to the mapping, you know. Yeah, so let's put that in there. Okay, sure. Now we can do interesting stuff. Now we can, well, we can first of all just create an integer. And if that is not used later on, then we'll drop that. Okay, hang on. That is a very common thing, I guess. you're pushing a drop. Some sort of, let's create a function for that. Push drop if not needed. That receives a builder, which will be a pudding body builder, and it receives this set of expressions that are needed later on. Boom, like that. And what it does is, if not, oh yeah, also needs an ID. If that doesn't contain that, then we just push the drop operation of that ID to do map that, and we ignore that. Amazing. So in here we'll actually do body.push, builder.push. That is already mutable. Yeah, push drop if not needed. Oh, and we need our own ID basically. Okay, you know what? I think that is more like a general thing that we can do down here. Push. Oh yeah, we already do that. Well. Maybe that was kind of an over abstraction. Factoring that out into a function. I'm gonna leave it like that, and we'll get back to that. Yeah, so here we have needed later on. All right. Yeah. So the int is always just an int. The string is always just a string. The struct now it gets interesting. We have the field value. Yeah, but we don't want to dupe all of the values. Yeah, it is weird that this returns an expression rather than an ID, so let's change that. And let's just do push, I guess. Yeah. And then basically in here we dupe those arguments that are needed later on. Yeah, those that are also needed later on. So if needed later on contains ID, something like this. Yeah, for every field, hang on, for every field in the struct we just do that. We get the field value. ID, and then if that ID is needed later on, then we'll push the ID in here. Okay, new plan. We store the dupes directly in here and do that separately. Yeah, let me maybe write something down. Also, the mapping between IDs is weird. I think we don't even need that, because we know that every expression immediately gets, like every expression gets at least one pudding expression. So I think we can just do the basically the IDs stay the same between yogurt and pudding. And we only insert expressions in between that. That add IDs is necessary. Yeah. Yeah, and the yogurt IDs are the same in the yogurt and pudding. The pudding only contains, generally, the pudding is also very similar to yogurt in terms of inspection. The only difference is that it contains additional dupe block instructions for incrementing and decrementing the frames counts of semantically every value in the pudding is reference counted in later on. Some of the reference counting operations are simplified. For example, if a value doesn't, if a type doesn't require any heap allocations, no reference counting occurs. It is copied. Okay. Yeah. Also, unlike other compiler stages, the pudding is built from the bottom up. Yeah, I don't know. That is probably something you'll figure out. But yeah, it is weird. Yeah. Okay, so we have a builder, which is a pudding body builder apparently. Yeah, we don't need any mapping. We just say, hey, I on the struct is just this. Fields are exactly the same. That is clean. So these are just the fields. Oh man, that is cool. Yeah. Okay, so if needed later on contains that field value, then on the DAG, which is the pudding DAG, yeah, we will put in there a dupe operation of the ID of the field value, something like that. Yeah, then here we have the struct ID, which is build.push, okay. And then all the dupe operations, they occur before that. So builder dot not push, but maybe I'll do that directly. Pushing these IDs. Maybe that's weird. I don't know. Yeah. I do want to this dupe and drop. Let's add 2 operations for that. Put dupe on a DAG. That seems fair. Then in here we can just say deck dot put dupe. Then we push the individual expressions and we return the struct ID in the end. Okay. Then the member expression. That doesn't really consume the original one, I guess. So this will be the okay, no, I'm gonna first create a new builder, I guess. And it turns out that the builder is kind of specific to how we how we go about compiling the function. So I think this actually belongs in the mapping in this compiler stage here. Okay, so the pudding body builder should not just contain a DAG and stuff, but instead I think it should I'm not entirely sure though. I think I'll just remove that entirely. I might do that. I might do that. Yeah. Yeah, sure. Yeah. No pudding bodybuilder needed. Instead, we just have the body here. And that is just a list of IDs. Simple. Honestly, simple. And so much simpler than before. So that dag dot push output puts a new idea into a dag. But what if we already know the ID because the mapping is a one-to-one mapping? I think we don't really support that yet. So let's add that. Let's say that we want to put into this ID a pudding expression. Yeah. Something like that. And that's just gonna do dag dot nodes, I think, dot set ID dot index expression. Yeah. Okay, so this would just be your body. Okay, it would actually be two pieces. It would be yeah, let's say we have something like this. And we have this surrounding yogurt fun, which we don't really need, I think. We can just do dag. Is the dag enough? Yeah, and down here we don't need some sort of builder. We just say rev body because it is reversed, and I think it makes sense to kind of have that constant reminder that this is reversed. I don't feel too bad about that. Alright, so here we do ref body. If not needed, later on contains ID. Then we do ref body dot push. Dag dot push drop of the ID. Maybe that should return the ID of the expression after all. Yeah. Yeah, that makes sense. mapping needed here. That's pretty cool. Then we say let's convert the function ID to a pudding. Is there enough? That would simplify things a bit. Yeah, this is just the ref body. Rather than finishing a builder, we just have the pudding body of that returns thing, of the params and of the expressions. I don't think there's a reverse yet, but we'll create that. Okay. Yeah. Now I need to put something into the mapping, because we don't have a mapping, we don't need a mapping. Here we have the params. For each of the body params, we check if we don't have a build push param or something. I don't just I guess DAG, which we have, yeah. Put a pudding expression that param. I am putting up param dollar and then the type. Yeah, that gives us an ID, and we push that ID into the param like that. Okay. Yeah, there's an error on the signature here. That is. Yeah, we'll probably get around to that, but first do the relevant, the interesting stuff, and that is we have this ID. Let's first get the corresponding thing from the function. And then based on that operation, we'll do something. If it's an int, then we will actually create an int expression. Yeah. So this right here, let's call it ref body, because it is really the reversed body. And that makes it kind of obvious that if this expression is not needed, then we should drop that afterwards. Something that for now I think we did here, yeah, let's do that in the function itself instead. Yeah, if that expression is not needed later on, and this, the ID will just be ref body. Oh, hang on, and dag.put under that ID, we will put that expression. Yeah, that's it. And then ref body.push ID. something like that. That's pretty cool. Similar here, dag.put under that ID we put this expression, and then we say ref body to push that ID. Amazing. For a struct, we have these dupes. I mean, what we can do anyways is do this. Either way, we want to push a struct expression. Yeah, and push that to the body. Yeah. Does this put still return something? No, it does not. That is fine, I guess. Okay. And then in front of that struct expression, for those fields that are not needed later on, those fields that are not needed later on, we will put those, and we will put a dupe expression into the DAG and then push that to our reverse body. If this is the last use of that expression, okay, it's not needed somewhere later, then we don't dupe that here, but instead we make the struct take ownership of that directly. But it does mean that now needed later on should contain the ID. Beautiful. Okay, and we're getting somewhere. And I could make this put also return the ID directly, and then just put that in there. I'm not entirely sure how I feel about that. Yeah, let's do that. Let's say this just also returns the ID directly, because why not? And then we can immediately use that in here. Okay, yeah, that's the struct. Then for the member, I think we'll actually dupe. Hang on. Yeah, the inner part of the member. Yeah, we might have a struct where multiple fields have heap allocations, and we want to I think the best way would be to drop basically not reversed, you say you need the struct first of all, so need it later on, but put the struct, the member, we need that. Okay, we will get one ownership of that basically. Oh, hang on. Oh, this is interesting. I think this is a very common thing we will have. It makes sense. Yeah, it may make sense to put that into its own function. Something like depend on something. Require. Yeah. Okay, so we will probably if we were to not have a reverse body but just a normal body, we would do something like this. If the member of is needed later on, then we push a dupe instruction of that member, because we need that member to still be around here. Otherwise we say, hey, this is the last usage of that. Then we push a, oh, hang on, not what I wanted to do. Then we will push a member instruction. That's kind of this. Hang on. Yeah, something like that. Let's get the type in here as well, because why not? Then in here we can just do type, and here we can just do type almost. In here we can do type and so on. Yeah, then we kind of push the member, getting the member. Then we dupe the off thing. Yeah, that would be body dot push dev dot put dupe of our ID. And we drop the original member. Something like that. This is what we need in here if we were compiling forwards. However, we are not, so let's flip that around. Oh man, it's kind of like this is a brain teaser code right here. Man, damn. Also, this is really a common thing, so I am gonna add some sort of require for that. Not, you know, push drop if not needed and stuff, because nope. Ref body is going to be a list of IDs, and then here this is called require this ID. Needed later on as a set. Amazing. And this does something. Oh yeah, it does this right here. So if needed later on contains the ID, and we also need the DAG. Well, okay. Yeah, and then in here we can just do web body dot require field using the DAG and the needed later on. Amazing. And we can do the same here. So yeah, web body dot require wow. Same here, we'll do basically the exact opposite. We don't need this. Yeah, we require, so rev body dot, we require the value, which will be the enum value, so that we can then use that in our thing. In here. Yeah. Oh yeah, and this thing does not really need to return an ID at all, because we don't need to do anything with that. In fact, we can just, like, this is supposed to just do ID dot okay. Even simpler. Yeah, here we do ref body dot push DAG dot put under this current expressions ID, just put the putting up enum. Then also require the value. That's pretty amazing. Okay, how does the switch work? I guess. I'm actually not sure. First of all, we have no mapping. And yeah, we dupe the condition, that makes sense. So we grab body dot require the switch condition. Yeah. Then we'll have the actual switch. Ooh, this is actually really interesting. For the individual bodies, like this is done, yeah. Yeah, well, someone need to track Like if a value is used in one switch branch and not in the other one, what do we do? I think we don't. Then in the other one, we want to insert a drop instruction right at the beginning, which is kind of, this is super cool. But yeah. Yep. Oh man. So we require the parameters. Yeah. Yeah, there are no, I mean, captures is just lambda.captures, that is match 1 to 1. Then for every captured thing we'll need to do something, but hang on, we'll also need to do ref body dot push deck output of ID to that operation, like that. Amazing, maybe. Ooh, yeah, and for each capture we'll just do ref body dot require that capture with the, what else does it require? It requires, not like this, or this, or this. It requires the DAG and need it later on as additional fields. Let's also add that here and here, because there's just incorrect code. What's going on here? We have this. Oh, it is a, oh yeah, field of value. Yeah, off is member.off. Value is just enum.value. Yeah, here we have a mapping. No, we don't. To pudding. This doesn't work, yogurt. Pudding this. Oh yeah, the body is weird in how its parameters are organized. I think, first of all, it shouldn't need a mapping. Maybe put that there, I don't know. Builder is not in scope because that is just graph body. Ampersand push tag dot push drop. This does not work because oh, it is put top. Yeah, sure. Okay, yeah, this is not a thing. Reversing a body, we'll need to make that a thing. But first I'm gonna look at the other expressions. In particular the call, that's gonna be interesting. So we already have the arguments. Well, we'll do that at the end of this case down here. We'll go with the arguments. We don't have a mapping. Instead, we'll just do graph body dot require that argument using the DAG and the needle later on. Something like that. Amazing. And this right here is just similar to ints, which is graph body dot push of DAG dot put of putting up type of our type. Oh no. Type. I'm gonna call it type now. Yeah. So that it doesn't conflict with this one. Yeah. This can be simplified a tiny bit at least. Yeah, then in here we need stuff. Yeah, the lambda, we don't need mappings. We just emit the lambda call, so that would be graph body dot push and dag dot put. We already know the ID. That's going to be a lambda call of that lambda. Yeah, and then graph body dot require that lambda. Okay, yeah, for the function it's gonna be graph body dot push dag dot put ID that call. Amazing. And for the built-in we will just push a instruction. So graph body dot push of dag dot put of the ID and here get up instruction until here. Yeah, that seems correct. Really intended. I know. Yeah, args is gonna be called args. Amazing. And same here, by the way. Args is called args, please. I don't like how verbose some of this is, but sure. Okay. Got that. Alright. Yeah, so then reversing the body. How is that? Is this needed? I'm honestly not sure, and I believe not really. But we'll see. So reversing the body. That's gonna be interesting. Yeah. Yeah, let's reverse that. How is there no standard library function for that? Let's see, standard lib mem maybe? There's ref iter, but that's it. I mean, can I do dot ref iter dot to slice, something like that? I hope there's a to slice on iter. Take the body, which is a list, I convert that to a slice, I iterate over that slice in reverse. Oh no, I can't. Sad. Nope. Is there, let me see, iter. Iterators are really cool. I think that makes, like, implementing iterators for Plum would also be super nice. Yeah, okay, so there is no way of kind of collecting an iterator to a slice or list or something. Let's do that, I guess. Or let's say the body is a list of IDs. And then yeah, that's fine. For ID and ref body dot to slice. Now let's just do that. Okay, ref body dot to slice dot ref iter. Basically do body push the ID, and then body is body dot to slice. Stuff like that. Boom. Until let's say terms is terms to slice, so we can just remove that. Well, that actually. Yeah, these are actually just expressions, not the body, because technically a body also has parameters and stuff like that. Okay, yeah, this is reasonably concise, I would say, and this is body returns. Okay, oops, don't know what I did there. Let's see. Oh yeah, switch doesn't work yet, by the way. Just thinking of that. 180. Here we go. So we have a function. We want to convert that function to, well, to pudding, I guess. So we create a DAG, we don't create a mapping. The captured variables, well, for each captured variables, I mean, we don't need that. All this. And instead, here we can just do from captures. And in here we make sure that we put an expression into the DAG with the correct ID. Stuff like that. Amazing. Yeah, this is the capture. I don't know, let's call it ID, because why not? Yeah, we don't have a mapping that we need. Simple, 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 simple. Oh yeah, set of needed later on. there's just going to be a set of IDs. Mutable, of course. Okay, yeah. Yeah, this switch is kind of an open question on how to deal with that. So we have the switch condition. Yeah, in the cases, I think for the cases we'll actually need to have I mean, this will be executed for each of the cases. So they will have this kind of reverse body in there. They will have a return thingy. And for every ID within that, it does stuff. The body does stuff. Yeah. It's kind of so I think in a switch. Let's think about this is wrong as well. Yeah. So in a switch, we kind of want to let's say we have like 2 or 3 variables or something, and we have a switch on multiple branches. One branch maybe doesn't use any variables from the outside. Then another uses one of these 2 other, variables, and the third branch uses the second variable. I think we kind of need to, we have this needed later on set. I think the first step would be to save that, to just store that set somewhere. Then, having that as the baseline checkpoint kind of thing, compile each of the bodies, and they should each tell you what expressions, like how that needed later on changes. If they, capture stuff from the outside world. If they, not capture like lambdas, but if they consume stuff from the outside world. And I think basically we want to look at all of these our own needed later on thing has to be the union of these sets. Because even if just one of these switch branches uses some value, we need to put that into needed later on, because then that value needs to be alive until the switch, definitely. Because we don't know which switch branch will be chosen. That means that the value needs to be there for this one particular branch that needs it. So then we have the set of values needed after the switch. And we have the kind of union of values needed to be there before the switch. And for each case, we know which values it needs. And I think then we just need to kind of cross-reference or check, like, are there any values, like for each switch branch, we check, are there some values that are not needed there, but that need to be available until the switch. And those values will drop them right at the beginning of the switch body. Yeah. That makes it kind of, we're kind of working against us a bit in the sense that here we convert the yogurt body to pudding, giving us a pudding body, but that essentially does this. Where it builds this kind of reverse body, it checks, well, these are needed later on, we iterate over these, we iterate over the parameters, stuff like that. And then it kind of reverses that body to be correct, and it returns that. And in the switch, we kind of want to add some expressions right at the beginning of the bodies. So it would be kind of more useful if the body was still returned. But yeah, I guess it's fine like this, because yeah, we'll figure out what to do about that later. Needed after switch is going to be needed later on dot, I think there's a copy function on types. I'm not entirely sure. Nope, apparently not. Or maybe seems to work. So this is basically the set of IDs that are needed after the switch. And then for each case, oh, hang on. Yeah, let's do this. Let's do this. I don't know, needed by this branch is needed later on dot copy. Amazing. Needed by branches. It's gonna be a map from string to a set of IDs. Yeah, and then in here we put this into the case, yeah, and we put needed by branches. We put under that key the needed by this branch set. Okay. Needed by any branches. That's just going to be a new set of IDs. And then for each entry in needed by branches, we kind of add all of them to the set. So entry dot value dot needed by any branches dot put all. Is that a thing? I don't know. Maybe not. No, maybe not. Okay. Let's just iterate over them, I guess. Or let's fix that first. Oh, there's an ampersand stuff. Okay. Oh. Let's see. So copy. How's copy even? Let me take a look at copy. Oh, I think that was actually like a compiler, kind of compiler generated thingy. Let me see. Copy generate compile copy fun. Yeah. So you can copy any type, okay. Oh, is there like a, let's see, standard library, standard lib mem probably has the, is there a copy slice of T? I'm more looking for references. I don't know. on, let's see, is there maybe... Is it in core, maybe? Nope. Light fuzzing. Maybe it's in fuzzing. Yeah. Okay, so there is this. Oh yeah. Okay, so copying an ampersand set actually copies the set and then puts that on the heap again. That's perfect. Yeah. Like, to be honest, that's kind of messy. Martinez. That is really messy. Okay, so needed by branches dot put needed by this branch. Yeah, that is sure. Yeah, put all doesn't exist. That's what I thought. So for ID in entry dot value, which is supposed to be a set, we can just put that ID there. Put a set. Oh yeah. Needed by any branch. Needed by any branch. Yeah, something like that. Yeah, I know that. Like this. What is going on here? Output. Right, we need to reserve space in the DAG in the beginning. Like that is a thing. Yeah, let's do that first. So in the DAG, we want to push placeholders, I guess. Down here. Oh. How do we know? Oh, I see. We can just do for I in 0 to, now comes the weird part, yogurt.dag.expose.len. We can just do dag.put. Putting expression dot, I don't know, uninitialized. That's even a thing. That is beautiful. So putting up at type some type never, something like that. That's not a thing. Oh yes, a thing on the current function. Yeah, it's called nodes. I see that, yeah. I see that. Yeah, it kind of ruins a comment. The IDs and the yogurt and pudding are the same. So we first reserve IDs for all yogurt expressions so that cube so that the cube drop expressions get bigger IDs, something like that. Okay, I like that. I really do. Okay, so to pesto. Okay, well, that is expected, I would say. Oh, look at that. This looks pretty cool. The playground, the main function now. Just as a reminder, well, I don't have that here, but before there were so many like dupe and drop instructions here. Now that is minimal. It doesn't use its argument, which should have ID 0. Well, hang on. So in the body for the parameters, we say push that parameter with that known ID. Yeah. Anyways, we drop the parameter to the main function immediately because we don't use that anywhere. That's amazing. And then we create this 2, we create this 1, we multiply them, which consumes these. And then we create the 4 and we call plus, which consumes this and this, and that gets returned. There was no need for dupe and drop instructions for like these mathematical expressions here. Yeah, and the argument gets immediately dropped. That is pretty amazing. That is super amazing. Let's see how that stacks up if I play around a plum. If I do something like introduce a variable. If I have, I don't know, b equals 3, and I use b 2 times in there. That is amazing. Oh, okay. So we create the b, which is 3, and the first thing is we want to multiply that b and 1. So we want to call this multiply function, but the multiply function is going to free, or like, yeah, not free, but drop the reference count of both arguments. And the 1 will need that later on as well in the plus function. So we dupe only the 1, not the 2, passing ownership of that to the multiply function, so that we kind of still have one ownership left of this, so that we can also pass that to the plus function. But here we don't have a dupe, because this is the last time that we use the 1, and the plus function will take care of freeing that. That is beautiful. That is really beautiful. Okay, let's do, I don't know, let's have a function that has a switch inside, because that doesn't work yet. But then we can kind of see how that, kind of more clearly see what we want to do there. Let's say we have some runtime known bool that would maybe be comparing a to 0. Oh yeah, compare returns like equals or less or greater. And in all these cases we do something different. Here we just return a 0, here we return a 1, here we return a 2. Now the interesting part, let's say we have 2 variables. Here we have 1 and we have 2. And yeah. So this one doesn't really use any of them. This one uses A, this one uses B. Let's see what happens. I mean, it crashes with a to-do switch because that's not implemented yet, but oh. True, I guess. True. Compare ints. Let's do that. Oh, from the built-ins package directly. Interesting. Equal is not handled because they are equal or less. Yeah, A is equal or less or greater. That makes sense. Okay, so we want to compile the switch. The yogurt looks amazing. We create these integers. Oh yeah, then we compare our argument. Oh no, hang on, what do we do? Wait, what? We compare ints with 1 and 3. That would be the 1 and the 0. Oh yeah, I was thinking let's take the argument, but actually this A shadows that A there. Yeah, okay, makes sense. I mean, I'm totally fine with this. So what we do is we switch on that, Yes. if that is less, then we just return this 1. If it is equal, then we create a 0 and we return that. If it's greater, then we return this 2. Yeah, okay. So let's maybe, if we have this to do in here, to do switch, let's just let this run and see what happens. It's probably not gonna be correct. But let's use the needed by any branch, and we'll see that it doesn't drop all of the values, because it just treats as, you know, if an ID, if a value is consumed in any branch, then I'm fine with receiving that, you know, receiving ownership of that value here. But in the other kinds of, like in the other branches where that doesn't get used, we don't we don't take care of freeing that value. So here stuff doesn't work because this is you know what, this is, oh, it requires a mutable thingy. No, hang on. Needed later on. Let's use that actually. I think that is fine. And also let's, I think actually though, we will need to kind of integrate this into the needed later on thing. Yeah, so for ID and needed by any branch, we do needed later on. Dot put that ID. Yeah, and in here, in between, this is where we want to, well, up here, this is where we want to kind of bridge the difference between these two. Okay, this is something. We have the 1 and the 2. Fair enough. Oh yeah, the argument is not used at all now because it's shadowed by our a, which means that it's immediately dropped at the beginning of the function as soon as possible. That's nice. Yeah, then we create the a, which is the @1 in here. We create the b, which is the @2. Then we dupe the a, because we use that both to compare that to integers here, as well as to return that down here. So we don't want this compare ins built in to free the int. Makes sense. So we dupe that, we call this, we switch on this result, yeah, which consumes that. Nice. Yeah, so then let's see if that is a less. Then we return 1. Yeah, but here we want to also drop the 2, because otherwise the 2 is never dropped. In this greater case, we want to drop the 1, because we are only using the 2. And in the equal case, we want to drop both 1 and 2, because neither are used. Okay, let's do that. Let's do that. How does that work? We kind of need to create new pudding bodies, I think. Yeah, so I think for every case, well, yeah, in cases, kind of need to do stuff. Diff to other branches, something like that. And yeah, what I want to do is take the, is there like a difference or a subtraction on sets? I don't think so, but basically we need the IDs that are in this set, in this set, minus, except all the IDs that are in the needed by branches, get case key, the IDs that are in that set. Yeah, kind of like that. There's the diff to the other branches, and then we want to insert drop expressions for each of these. And so we're going to build a list of that. And, well, for every ID in that diff, we will add an expression to the DAG and put drop of that ID. That's going to return us an ID that we then add to the drops. Yeah, and then we want to change the cases. Oh, and this is not mutable, I guess, this case. Yeah, okay. I guess that's just the cases dot ampersand dot put case dot key, and as the value, we will just take the pudding, a new pudding body that is very similar. That has params, expressions, and returns. This is just case.value.returns. This is just case.value.params. And this is our drops plus the case value expressions, which I believe is a slice, so we need to kind of, I don't know how the plus operator works for lists or slices or whatever. Yeah, this doesn't work. Let's see if there is like a diff function for sets. Let me go into any standard lib module, open the set. Okay. Yeah, okay, no. No, there was nothing like that. Which is fine, to be honest, that is fine. Yeah, set diff to other branches would be a set of IDs. That for every ID needed by any branch, we do if that is needed by this branch is that. If not needed by this branch dot, if the ID is not needed by this branch, then we will add that diff to other branches and dot put the ID. That is dense code. I think this can be kind of separated a bit, at least. Yeah. There are the individual cases throughout the IDs that all branches need. And by the way, I think, they're needed later on. We don't, we use that down here, but every ID needed by any branch, we immediately add that there. So I think we don't need this one. We can just use needed later on. And not have this. a branch doesn't use IDs that other branches use, drop those immediately. We'll drop those at the start of the branch body, something like that. Yeah, this doesn't work because it only lists and slice. It does work for lists and lists. So can we do something like a list constructor takes a slice? Oh no, that's gonna create a list of slices, like well, right? Yeah. Is there like a to list maybe? Nope. Nope, not really. Oh, maybe there is. Oh, amazing. So we'll just take that and then say to slice. I like that. Okay, that is kind of amazing. Yeah, that's an old arrow. Let's see how the pudding looks. Well, no, it doesn't. Doesn't look correct. Okay. But why not though? Hang on, let's go through this. We lower the individual cases. Makes sense. Yeah, then we put those IDs needed by any branch into the needed later on thing. And then we do needed by branches.get. Get case.key. Calculated diff. That makes sense, I believe. Okay, let's just print stuff and see what happens. Let's maybe print case key needs needed on this branch. Oh no, my T is done. Yeah, so less needs, well, 6, and we need that later on, yeah, and then 1. Seems correct. Yeah, that seems correct. Actually, we can even simplify that further, because we don't need to copy the original one, we can just create new ones, because we know that none of the expressions later, used later on, will be produced by this body right here. Instead, there will be a new expression. So we can just say this is a new set of IDs. That makes sense. That is really cool. Yeah, and that also kind of like for really big functions, you don't copy stuff around. Like in general, we don't copy any set. That is super cool. Okay, so we have stuff. We have less needs the 1, equal needs the 5, greater needs the 2. Let's see. Oh. Yeah, okay, maybe not like this. Yeah, maybe let's undo that. Yeah, I don't know. I mean, yeah, it does make sense, I guess. Like if I don't know, 6 for example is used down here. Like even if like the 3, I don't know, is used later on in the function, that needs to be respected within these bodies, because now they can't just consume the 3, they have to dupe that beforehand. Okay, so at this point in the code, we need to have 6 and 1 available. Yeah, equal needs 5. And 6 and 1. Interesting. Greater, oh, okay. I think the copying just doesn't work. I think the copying doesn't work. Well, doesn't really copy stuff though. So, that is sad. Why doesn't that work? We have a... How does that even work? Compile copy fun. What it does is it doesn't work on opaque types like addresses. That's nice. For structs, we copy the individual fields. Makes sense. For enums, we switch and then create something and copy the payload. Okay, also makes sense, I think. Then we return. Okay. But for sets, what even is a set? A set is just something wrapping a map to nothing. So this would say map.copy, and map.copy would call, is there like a map, like a copy file in here? There is. Interesting. So we create a copy, and then we say, we really create a copy, interesting. We say for every entry in the map, in that copy we put the entry key.copy and the entry value.copy. In our case the key is just a string. Yeah, the value is an ID that can be copied because it is a struct that contains an index int. Yeah. That's weird. Needed later on is not really modified, is it? No. It's just copied here. So that's going to print that out as well. Yeah, needed later on. Needed later on. Sure, print that before we copy that. That should stay the same. And it doesn't. Because needed later on is a reference. Needed later on is a reference to a set of IDs. But that means that this function matches. These fallback functions are only chosen if no other function matches. But because this is a reference to a set, this function matches. So we should take that reference, dereference that to get the set, and then do set.copy.put on heap. yeah, copying a set should just copy the struct, which contains a map, which should just call copy on the map, which should call this custom copy function, which should call copy on the individual elements and put them into this map. Am I missing something? Need it later on. I don't know. Like this should perform it like a deep copy, you know? Allocate memory and everything. Need it later on 6, need it later on 6, 1, need it later on I don't know what to do. I don't know what to do. I mean, I guess let's just create a new set and start using the copy thing. Just for every ID, and you don't need it later on. We just put that into the set. See what that does. Oh, that is interesting. Okay, need it later on 6. 6, 6, that stays at 6. Less needs 6 and 1. Yeah, 6 in here and 1 in here. Because it uses that. The equal needs 5 and 6. 6 and 5. The greater at the uses 6 and 2, yeah. And that means this drops the 5. What is the 5? Oh no. Yeah, okay, nope. And the 2, that is correct, yeah. This one drops the 1 and the 2, that's actually already correct. Yeah, but the 5 doesn't have to be dropped because it's only defined in this branch. Okay, so I guess we will do something. Need it later on. That seems to work. That seems to work. I think we'll need to compare these. I mean, maybe that is actually fine, but whenever a variable is defined, Oh, hang on, in here. Then we're gonna remove that from needed later on. Oh, hell yeah. Oh, is there a... I think there is no remove. Ah, God. How do we... Oh, man. But yeah, I think it makes sense to... Now, when we have this, we should just remove the ID after it's defined, because the code above that doesn't even need to care about that ID being there. Yeah, okay. So there is no removing things from sets or hashes or hash maps. Okay, I've added a remove function for sets. Although I should say, we kind of need to think about if that is not even in the map, because that doesn't work yet. Yeah, when running this, it says ID 0 is not in the map, because apparently this is not used, which is fair. So what we do here is we do something. Not sure. I guess. Hang on. We compile that ID to pudding. So what we do is we get the expression. Depending on the type of that is not needed later on. Then in that reverse body we insert a drop expression for that. That makes sense. Yeah, else if that is needed later on, then at this point we can remove that. Because this expression cannot depend on itself. And earlier expressions can't depend on that as well. Okay. So when we say to pudding on a yogurt body, oh, hang on, there's to pudding on a yogurt ID. The body is down here somewhere. Here we also do a remove. Do we? Oh, we do. Yeah, that is not needed later on. Then we immediately drop that. Otherwise, we remove that from needed later on. Yeah. Okay. Oh, this looks fine. So we define 1 and 2. You know what, I'm tending towards actually making the example a bit more. Let's call this true and bar. Yeah. Okay, and if I don't know, if bar is not used at all, this 2 right here, then that should be immediately dropped. Yeah, we create the 2 and then we drop that immediately. but because it's used down here, only because it's used down there, we kind of keep these values alive until the switch. So here we have 1 and 2, these are foo and bar, and we keep both of them alive until the switch, and then in the switch, because the less branch only uses foo, it drops the bar. The greater branch only uses bar, so it drops the foo, and the equal branch, it uses neither of them, so it drops foo and bar. Oh, that is nice. That is nice. And we can even say something like, if the function always returns foo, then things change. Oh, that's actually really going to be really interesting. Yeah. What? No, we don't drop foo in here at all, because we still need that down here. And the less function drops bar, the equal function drops bar, hang on. I think this should dupe the 1 in here. Yeah, it should dupe the foo. That is super cool, honestly. What? Needed later on dot put. Oh yeah, that's not the only thing. We also want to, what we really want is we want the reference count of that to be available for the body to return. So we want to require that body returns using the DAG and needed later on. That's really good. Yeah. Okay, so we have foo and bar, and the less returns foo. The bar is used in some of the branches here. So it is kept around to the switch, and the switch is responsible for freeing that. So in the greater branch that is just returned, but in the equal branch that is not used at all, so it's immediately dropped. And here as well, it's immediately dropped. The foo is used after the switch, so the switch is not responsible for dropping that. Which means that the equal and greater branch, they don't use foo, they don't do anything with that, but the less than branch, it uses foo, so it dupes that before evaluating that. That is amazing. That looks so... It feels like this. This is why writing a compiler is fun, you know. You create this kind of thing that has really simple principles, but it kind of works, like everything nicely fits into each other. Like this is cool. This works like a mechanical clock or something. It's something like you want to play around with this. What? That's cool. That is super cool. All right, yeah. Let's try something a bit more complicated. Let's say, yeah, let's remove this in favor of the usual example of the make list and then sum that or something like that. Make a list with length 2, and please give me the sum of that. I'm so interested. Let's see. Oh, what that is. Does that make sense? Hang on. Oh yeah, it's hexadecimal stuff, so yeah, probably makes sense. Well. Okay, so this is the list sum function, for example. And remember, before there were so many dupes and drops in here, like so many. Now we just switch on the value and we return the result. Makes sense. Oh man, that's cool. Yeah, in the empty case we don't. we don't need to drop anything. Okay, I'm not actually sure that is correct, because I think we'll need to take the payload of the enum either way, regardless of whether there's binding for that. Because the branches need to take ownership of the enum payload. Okay, but in the more case, we dupe that. Okay, so that we can then get the item. So that we can then drop that. Okay, I'm not sure about that one. That is like that works, but it does not seem optimal. I can, kind of, I'll look at that. Okay, but we dupe that. Sure, we get the item. Yeah, we dupe that item. And drop the surrounding one. Why? What? Oh, I see. Yeah, this works at least. Yeah, we may want to optimize that further. True. Yeah, here we get this one, and then we dupe that one, and we drop that. Yeah, and this the point is this struct access doesn't take this, I think, doesn't take ownership of the two. Or it doesn't drop that immediately. So that's why there's an explicit drop of the two after duping the inner value, the rest. Yeah, okay, I guess. I'm not too convinced about that, to be honest. Well, okay, but then we call the sum function with that rest, and we call the plus function with the result of that and the item that we got. Yeah, okay. Yeah. That does seem correct, I guess. It is kind of weird. I'm not sure what to do about that. Let me maybe adjust how the member is, how that works. So drop the member off. Thing is, if we, here we require the member for us, which means we may dupe that member just to drop that later on. That does not seem smart. So rather, I think here we need to do something custom. So basically, if needed later on, if that contains the member of, then we'll do something different. Else we'll do something different. Else we'll do this. Otherwise we do this. And both of these, I'm going to simplify both of these to, only do the necessary stuff. So if the .off is used later on, then we don't require that here, and we don't drop that afterwards. So we just, reading from the bottom to the top, we just access the member, and we dupe that member. Makes sense. Otherwise, we definitely otherwise we require that member of to be kept around for us, basically. Yeah, so that we can then access the member, dupe that member, and drop the original one. Makes sense. Tiny bit more useful code. I don't know. Let's see how this looks. Yeah. So we just say we take to.item, we dupe that. Makes sense? Yeah. Then we take to.rest and we dupe that. So this was a struct containing two fields. What we've done is we have essentially duped both of these inner fields, and now we're dropping the original struct. Perfect. Like you can't do it any better than that with the current primitives of this. We may want to add some, destructure the struct into multiple things to kind of retain the ownership. But I mean, yeah, that's future work, if anything. Okay, so then we take that 4, yeah, and we take that 3 and consume both of these. Okay, that's perfect. Oh yeah, one thing I wanted to look at is the bindings of structs. So if I do something like isEmpty, and isEmpty takes a list, with syntax, yeah, takes a list of t, I don't know, and it returns an int because the main function needs to return an int, and it switches on that list if that is empty. Then it just returns 0. If there's more, then it just returns 1. That should also free the list. And I think currently it does not. Let's see what happens. Here's the main function. Yeah. Drops the argument because that's not used. There was so few dupe and drop instructions in here. It's nice. And this calls the isEmpty function, which is defined in here. Yeah. And it takes this 0, which may be some big ass data structure. It switches on that, fair enough. And then we have these two variants. They need to accept a payload. They need to. Yeah. Question is, at which point should they accept a payload? We can, like, I don't think the pudding is the correct compiler stage to introduce that, because the pudding is basically the yogurt with drip and drop, so it should also be there in the yogurt already. You know, these bindings, these parameters for the payload. Yeah, maybe in the conversion to the yogurt, or in the conversion to the what is it? To the egg may also be. Yeah, so let's see. In here what we do is we take the case.value, which is the switch case. Yeah, and we compile that using some, you know, some mapping. Okay, sure. And I guess that returns, that is defined down here somewhere. Maybe not. Maybe not. No, it's defined up here. Okay, sure. An egg body. I mean, we can already do that in the egg, so I guess let's do that here. Oh, that is small. Compiling a function. Basically, if we have a switch, then we want to compile the individual cases. Beautiful. If the case expects some payload, then we say the payload type is that. We can do that anyway. We don't need to have a binding for that. And I think we'll also add a payload either way. But only if there is a binding, then we'll make that visible in the code. That seems sane, I think. Yeah, if that doesn't... Okay, so the source of that is kind of ambiguous. I see that, okay. So maybe have an else branch where we just say, you know, push a parameter using the switch percent source or something. As the default, okay, this is an ID, the other one not, okay. So I guess let's just ignore that. Sure, we can do that. That is something. That is indeed something. So what's going on here? This is empty thing. Oh yeah, this looks a lot better. We have a value, we switch on that value. If that is empty, we just drop that. If it's more, then we just drop that. Perfect. Yeah. Amazing. Then kind of wondering where do things go wrong, because this is obviously the wrong result to get from that, you know. Why though? cast true to true or false. What's going on there? That is strange. That is strange. Okay, let's see if this, let's just go through these functions and see if they look fine. So the main function drops its arguments, it creates a 2, it calls make list of int with that 2. Make list of ints is defined up here. It takes an integer, it creates a 1, it dupes that, it calls compare please using that argument to 0, switches on the result. If that is true, then it doesn't use the original length anymore, so it drops that. It drops the payload, which is an empty struct. It creates an empty struct that is supposed to be empty. It creates this empty thing, and then it casts that empty to that. Sure, using that. And it returns that. Perfectly fine. In the false case, it doesn't use the payload, so it drops that. It has the 42, it has a 1, it calls minus on the original argument. That's consumed thereby, and the 9, the 1. So then it calls make list with that result. Then it creates a struct with that rest and the original item being this 42, which is thereby consumed. Makes sense. It creates a more variant using that payload. It calls the cast of that more thingy to that with 13, and it returns that. Okay. And here we cast that to something, to a simpler representation. Okay, I guess. So all these casts, they may be interesting. We have cast from empty to something and from more to something. Yeah, the equals function is here. It just calls compare int, and then it calls this is equal on that result and returns that. Perfect. The is equal is defined up here. Yeah, it takes an ordering, switches on that ordering. If that is less, then it constructs this false variant, casts that to a bool. Okay, if that is equal, then it creates this true variant, casts that to a bool. If that is greater, it creates the false variant, casts that to a bool. In all cases, it drops the original payload, makes sense. And here is casting that false to the bool, where we switch on the false. There is only one possible case, which is false with a payload. So we then create a false of that payload of the type true or false, and we return that and return that. Okay. Yeah, I checked that, I checked that, I checked that. Then there was this is empty. I'm not gonna look at that yet, just yet. Compare ints, I had that looks fine. Another cast, yeah, this is the one I was looking for, the true. When we switch on that true, there's only one possible variant, which is true. We construct an enum, return that. The minus just calls the sub-ints with those same arguments. Okay, now the casting functions. First of all, casting empty to this big thingy means just switching on that empty, that it can only be empty with no data. So we construct an empty of the correct type and we return that. Okay, and then the more thing cast this that switches on that original more thing. That can only be more. We construct a more of the correct type with that same payload and we return that. That is fine, yeah. And then we do this, casting this enum of empty or more of something to this other thing. Okay, so we switch on the enum. If that is empty, then we say this is empty of the correct type. Perfect. If that is more, then we have this struct of rest is empty or more of 2 up of the item. Yeah, and we cast that to... Oh, hang on, the original one was something else apparently. It was this. It was the rest is empty or more. I see. So more unwrapped, basically. We create a variant for that. Okay. So let's look at this cast from the struct. Because where's that happening? We have this struct. No, that's not it. It is here. Yeah, we receive some 0. We access 0.rest and dupe that. We access 0.item and dupe that. And then we drop the original thing. So now we've kind of unwrapped, like unpacked the rest and the item. And then we drop the original one, yeah, okay. And then we just create a struct with the rest being that. Yeah, and the item being the 2. Seems correct, although I should say it is like unfortunate that this that this even exists. This type, I think types should be simplified as early as possible. Yeah. Okay, but this looks fine actually. But the result is wrong. Why? Yeah, I don't know. Let's look at the pesto maybe. But the pesto is even more, even bigger than this one. So I don't know about that one. I don't know about that one. Hang on, let me check something. Let's check that. Not playground is empty. That the sum is still working. Okay, the sum works. How about the length? Probably also works. Yeah. Only is empty a string. That is strange. That is really strange. What? I don't know where that is going wrong, to be honest. I mean, even with bindings, that will still fail, I guess. I hope. Otherwise we did something really wrong. Okay, yeah. Okay, I don't quite know where that is. Like, why is that buggy? I think the 333 is the kind of thing that we pass to the main function. Yeah. Let's also print the result in hexadecimal, because why not? Yeah. I mean, not that that makes any difference, you know? Is this 100? Is that like a little endian encoding? I'm not entirely sure. Yeah. How can that be? Oh well. I mean, that really is unfortunate. Let's maybe go into these kind of weird struct casting functions, I guess. Yeah, that is this thingy. Oh no, this is the entire cast. And what? Alright, now we have explicit drop functions and so on. Oh, how much fun. Actually, so this takes as an argument this one, a struct containing that. So we take the rest, we dupe that. then we drop that. Original one. Not entirely sure how that works. I have no idea. I have no idea on how to do this. I mean, yeah, this looks sane, this looks fine, like, all of that looks nice and correct, but it isn't. And I don't know how to, what to do about that. Let's maybe simplify that. Can we do that without heap allocations and use the same kind of error? Can we just say, oh, please create an empty list, you know, like this. Oops. Like this. Maybe. Does that same error still happen? That would make things easier, perhaps. Yeah, we don't have any sort of type inference yet. So we should, in this case, say, hey, is empty is not, that would match, you know, but we don't know the T. Or, yeah, but we can just say we have some more thingy with an item that is 2, and the rest that is empty. I know that works. That is more. That's weird. I mean, make list of 2. Yeah, let's try that out with a make list of 1 and see if that's still... It's not yet saved yet. Yeah, now let's save that. Let's see if that error still happens. Should add some sort of make file that we don't rebuild the compiler every time I just change something in the program. Okay, that works. So this really is a problem here. Let's say list equals that. More with item is 42 and the rest is, you know, make list of 1, which would be that. Oops. Which would be this. Of make list of 0, which is empty. And then in here let's just say list. Should result in the same thing, I believe. Yeah. Okay. So let's maybe even inline that. Oh, hang on. Then we don't cast that to a heap allocated. Let's try that still. It doesn't hurt to try. My assumption is that this will work. Even better, yeah, true. I mean, yeah, that works. I'm pretty certain that that works. Yeah. Okay, that is not surprising. Does the list even have to store numbers? Perhaps not really. So I'm going to simplify some of that. Okay, that still fails. Let's try, rather than a list of some type T, let's do, I don't know, foo is either empty or small foo. Boom. So basically a linked list, except it doesn't really have any data. And this just accepts a foo, and this doesn't have to be that, it just stores the rest. Well, I'm not even call that rest, it's just that. So here we have a more of empty. Same error. Okay, I think this is, at least this is significantly simpler. Yeah, we can also remove these because they don't really make a difference, I guess. Okay, so at some point that is not working. Okay, now the pesto looks quite manageable to kind of review in its entirety. Oh man. Okay, so let's look at this first. Casting an empty to empty or more. Which is recursive. Which is this. It is, yeah, it accepts a struct with 0 being of this type. Makes sense. It unwraps the argument. Then it switches on that. It can only be empty. So here is the payload, which is an empty struct. It constructs a new empty thing with that empty struct, but of this type. Returns that, returns that, returns that. Okay, that looks fine. Yeah, the main function. It gets the argument, should be 100. Has this empty thingy. Hang on, is the argument even used? This one. No. Oh well. I was wondering why is it not dropped, but it's an integer, so I mean we don't need to drop integers, but that's why. Okay, so then it creates an empty variant with an empty struct, wraps that in a more, wraps that in a more, wraps that in this struct with a 0, so we have arguments, and then it calls the cast. With that. Okay, yeah, then it has this. This one makes sense. Then it has this puts that into an arguments struct, and it calls foo with that struct, returns the result. Okay, so I think the interesting part is actually just the casting and the foo. The foo unwraps the argument, switches on that is either empty with no payload. In that case, it just returns 0, or it is more with a pointer. Interesting. In that case, it actually loads the pointer, which will again be of the same type. It calls, oh, this is interesting, it calls a drop. On the original 5, hang on now. Oh yeah, okay, I see that. That makes sense. So 4 is a pointer. Oh, but that is never freed, is it? I think the foo actually behaves incorrectly. It takes ownership of this one right here. And that is this. It's an inline struct basically. If we see it as more, then we have the pointer. We load that thing. Correct. And then we drop that, but not the original pointer, the 4. That memory is still around. Then we return 1, okay, so that's fine. Well, yeah, okay, so this is something I'll have to think about. Another place is, oh, we have several casts. I mean, sure. Yeah, this can only be more, so we switch on that. That is more with an empty thing inside. So we cast that empty to an empty or more. Amazing. We push that on the heap, put a new more thing around that, return that. Okay, perfect. How did this work? We have this empty thing. Oh yeah, it just returns the empty thing of the correct empty. It makes sense. Yeah, and this will be pretty similar, just taking the 0 thing, switching on that. That can only be more of this nested thing. Casting that, okay, calling this cast. Putting that on the heap as well, returning that. Okay, perfect. Then we have this drop here. That is hopefully correct. Let's see, we switch on the original argument. If that is empty, we do something. We don't do anything actually. Yeah, if it's more, then, well, we drop the pointer, makes sense, returning the new reference count. And we have this int, we call compare ints of this new reference count of 0. If that is less, we don't do anything. If it's greater, we don't do anything. If it is equal though, well, now we load the thing behind that pointer. We call drop on that. We free the original pointer. We don't return anything. Okay. Yeah, that seems fine. So this is wrong. Okay, because we need to kind of drop the original struct. Not the payload of the struct, not only the payload of the struct. Oh man, okay. I guess that is something. So what is supposed to happen here? If not this, you know. I think if the I think in these, if the switch is the last usage of some value, then we'll actually need to drop the original value here inside these branches. And if we use the payload later on in that branch, we should still only, like dupe the payload, I guess, and drop the original switch or something like that. Yeah. Okay, yeah, I don't know. I think I'm gonna stop for today. I need to have a clear mental model of how ownership behaves for member access and structs. That is on my to-do list. I'm gonna think about that. And yeah, maybe some meta thinking about how I can debug stuff like this. Because at least, even if even if it leaks memory here, because it drops too few elements, that should still work though. Like converting that to waffle and to bytecode should still return the correct result. So I don't know what's happening there. I'll think about that. Yeah. Alright, I'll first try to get some more precise semantics around the switch and how values in the switch are supposed to be dropped. And also in the regarding struct member access. Yeah, so I think if there is a member access, currently we are basically duping the surrounding and currently we are, if the struct is used later on, we just get the member and we dupe that. That is perfect. But if the struct is not used later on, then what we do is we and what do we do? We take the member, we dupe that, and then we drop the surrounding struct. And that is not super efficient. Like you could, for example, say we want some sort of differential drop. Here, drop all struct fields except the struct field that we extracted. But I guess for now that is fine. I think it's fine that the struct access itself doesn't consume or doesn't do anything with regards to duping or dropping something. And same with the switch. I think in the pudding, the switch statement shouldn't do kind of an implicit dupe or drop. No, that should be explicit in the code. So I think for every enum case, for every switch case, we should drop the original enum value and dupe the member, at least something like that, So let's see, we have the switch down here. And the last thing that we do is we require the switch condition, which means the switch condition must be available here, and we kind of say, hey, if the switch is used later on, we will use this place to dupe the switch. And that makes sense, I think. Yeah. But then inside the individual cases, yeah, I think we should also, for the drops, we should also put drop the original condition and then dupe the payload. But the other way around. So we take the payload, which will be the params 0, and we do deck.put dupe of that thing and a drop, and those will both be IDs that we take. Yeah, let's see how that works out. And yeah, that is not optimal in several cases. But I'm not claiming it is, so yeah, here for example, oh no, maybe that makes sense. So we have this empty payload, we dupe that, we drop the surrounding switch, and then we also drop the payload because we don't need that. Yeah, that is certainly an interesting behavior, I would say. But I guess it's fine, yeah. Oh, look at that. Like, okay, something in this, like, something is really going wrong in the waffle or bytecode side. Probably the bytecode, because the waffle is usually pretty verbose, pretty well verbose as well, but also pretty well structured, kind of. It is still the compiler stage with kind of readable, kind of, yeah. I mean, this looks fine, I would say. I don't know about all of the individual things in here, but yeah, look at this. We dupe some value by doing something, by getting a byte out of that, switching on that. If that is 0, then we don't do anything. If that is 1, then we do some stuff. Yeah, we load the first part, which will be pointer, and we add, and we load 8 bytes from that. That's the reference count. We add 1 to that. Then we store that reference count back into that same memory address, yeah. And we do something. Yeah, okay. So this is, yeah, this is fine, I would say. Nice. that is super nice. That's fine. Yeah. So try to use a jump table of length to index something. Converting that to bytecode apparently doesn't work. So let's maybe print the instructions that we are running. That should give us a rough indication of. Well, that is a pain to debug. I know that, but it may make things more understandable. Oh god, this is a lot of stuff. Alright. I'm also wondering, like, did I break something right now? Or was that same thing broken before? Because, you know, taking a list and taking the length or the sum, those things still work. So I'm really not sure. Oh yeah, the builder is now in. I mean, this is pretty much independent. You know, make every switch case take a param. Yeah, what did we do in the VM mode? We just uncommented that. That doesn't count. Yeah, this is. I'm sure we can do that, and that is also useful. Be smarter about ref counting. Okay, you know what, let me check out a previous version, which is, I guess this. Yeah, let's check this out. Ugh. There was no checkout button here. That would have been convenient, you know. Oh yeah. Hang on, what else do we have here? We have the playground. Okay, I want to keep that actually. This one, I don't care. I really don't care. Printing the egg versus not printing the egg. I mean, come on. Yeah. Now, does that still work, or is that something weird? Okay, that seems to work. Well, that makes sense. That works. Okay. Why? Why does that work, but this doesn't? Like, I mean, this code should still be valid. I really don't get it. Try to use a jump table of length 2 with index 208. That is either here, length 2, or it is here, or it's here, or it's here. really get that. I don't. Try to use a jump table of length 2 with index 208. What now? How is that happening? I really don't get it. Man, I don't get it. Maybe I should write some sort of interpreter for the waffle that would at least, you know, maybe that's actually cool. I mean, you know, that the waffle is quite low level already, so it should be doable, I think. I don't know. I could also optimize the waffle, kind of remove a lot of the boilerplate that is in here. That would work as well. I mean, currently, you know, logging the instructions tells us nothing, basically. Yeah, no. There is just so much stack stuff going on. So many operations here. That's just crazy. Yeah. I mean, I can maybe kind of make out what's going on here if I try really, really hard. I don't really want to. But let's see, we have the main function. Oh man, okay, so we take eight from the stack. Then we push the byte 0. The byte 0. Oh, is it this one? Probably. I see, so this is this one, and then this one is just the byte 0. Then we push 1 from stack and offset 0, that is this one. Okay, yeah, and then a byte. Then we push 2 from the stack, push a byte. Okay, we push that entire thing. the stack. We push 7 bytes of padding. Push a 3-byte thing from the stack. That's the more of empty. And now we want to cast that, I believe. Let's see. Yeah, we cast that to something else. So what we do is we cast that by pushing the entire thing to the stack, pushing some padding, pushing that entire thing to the stack again, then keeping the top 2 thingies, removing the one below that. Oh, hang on, maybe the opposite way. Yeah, keeping one, popping the 2 below. Okay, so we switch on the outermost enum with a jump table with a 1 variant. Oh, who would have thought it is a more variant. So we push that entire thing again, we pop the outer one, so now we have the payload, those 2 bytes. Push padding, we push those 2 bytes again. Now we want to cast those 2, the more of empty, to something else. And we can see that in the code in here. Oh, hang on, in not there. In here, this one. Yeah, that will look pretty similar. We push those 2 things from the stack, we push padding, we push them again, sure. We pop the one below the top to get the outermost, which is the more variant jump table with only 1 thing. We push that, we pop the tag, giving us the payload, which is 1 byte. We push that byte, we cast that empty thing to that. Okay, so we push that, we pop that, the payload is empty, we push padding, we push 1 byte, the 0. Oh yeah, this is the newly constructed enum. That is the 8 bytes of padding and then a 0 indicating this is the empty list. Yeah, then we push that again, that 8 byte thing and then the 1 byte. That stack isn't aligned right now, that's weird. But okay, sure. And then below the top 9 bytes, we pop another 9 bytes. Okay, we jump to the end probably of that inner switch. We're like, okay, pop things, and below the below the top 9 bytes, pop 10, pop 1, and then we return. Yeah, the 10 were the local variables, the 1 was the parameter to our call. We return to the outer cast. The outer cast has now successfully cast the empty literal, enum literal, to empty or more, aka there is no padding in front. 8 bytes of padding, then 1 byte of the tag, 7 bytes of padding to align to 8 bytes, whatever lies 17 bytes back, whatever that was. Okay, and we push that, and then we push the 1 byte that is 8 bytes back. This just literally pushes the number 17 and the number 8. I see. That's the alignment, that's the size of the thing we want to malloc. Okay. Okay, we do stuff. Yeah. And then at some point we jump out of that switch, we return. We again allocate 17 bytes, okay, boom, 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 we jump out of that switch and we return back to the main function. Here we now call the foo function. Makes sense. That pushes some padding. Yeah. That pushes, yeah, basically copies the enum that is there. Copies that again, I guess. But then only keeps the top byte and removes the lower ones, aka the enum tag. It jumps on that. Yeah, we push the 8 from the stack. Okay. Oh yeah, and we pop the byte, leaving us with the payload. Okay, the payload, then we push an 8, we add both of them, because there's a reference count in the front. Now we skip that. And we take that pointer that is there. We also add 0 to that pointer. Sure, and then we load that. Boom. Makes sense. We've loaded something from the heap. However, I don't know how many bytes to be honest, but sure. Then we push another, and we push the pointer again. Yeah, plus 8, the number 8 literally, and we add those two. Okay, loading the single byte that is there. Fine, and then we below those 9 bytes, we pop the original pointer, push the padding, push that thing again. We call ourselves, I assume. Yeah, that again jumps, loads the thing, the inner thing. You know what would be helpful? Seeing the stuff, like I know we have this, but in here let's just also print the byte. Okay, so running this instruction, let's just print the byte here. Yeah. And down here, let's say let's do that. Yeah. And maybe let's say rather than this, we'll just have some sort of VM log function. Of some string, and then we can easily disable that, like comment that out. And then in here I can just use VM log. Yeah, it does mean that the string is built every single time, like we can't comment that out, but meh, so be it. Running some instruction, and then we immediately see the effects of that. Yeah, I kind of want to write the under push byte. I want to see the int that we just pushed. There was push byte, there was push int. There is pop int. Yeah, this kind of this. Let's maybe have some sort of get int, maybe. Then this is just vm dot get int offset 0. Yeah. And then here we can just do get int at offset 0. And we can also, by the way, do something. And what was this before? Stack len minus 8. Yeah, I think this also needs to set 8 bytes. Oh yeah, and down here let's do the VM log of that. Oh, it's a, oh, makes sense. Shouldn't even need to be mutable. Oh. We could also do the same with bytes. Like some sort of get byte. And that just does this, basically. Yeah, returning you a byte, and it does get data set len minus offset minus 1. And then you can just do the m dot value is the m dot get int at that offset, and then the m dot push int of that value. Or we can just print the value. Here that would just be the get byte at that offset. Amazing. Yeah. I mean, this is kind of useless because it is already in the instruction, I guess, but no. Yeah, pop something. Okay, sure, pop below top. Mm-hmm. We can maybe just print the byte. Yeah, these don't need mutable VMs. They don't. That one needs to be mutable though. Yeah. Okay, yeah. So we do stuff. I guess there was a lot of stuff going on here. Let's see, we create a lot of zeros. That is certainly a number. Oh, because it's padding, that makes sense. Yeah. Okay, and then in here we have pop 8 from stack. And push 1 from stack. Push 1 from stack. Okay. That is a 0 apparently. Okay, but that is fine, that's just padding. Yeah, then we malloc stuff. Oh, that. Maybe that should return the address. I think that would be pretty cool. You know, seeing the address right there. I think like this is the kind of thing that really makes things nice. You know, having these kind of debugging tools, these kind of meta things that make debugging easier. Those really pay themselves. Like, yeah, it takes some effort to do something useful there, but it's worth it. Okay, so let's see. So looking for the kind of malloc stuff. Okay, that's here. Malloc, oh look at that, returns this address. That's cool. Then we push a 1, we push 8 from the stack. Some sort of padding. And 1 from the stack, more padding, okay. Then we push this right here. I guess that's the address. Yeah, because we add 0 to that. Push the 1 and then we call store. Okay, perfect. Alright, then we do push padding. We return, then we malloc something more. And look at that, we have that on the stack as well. So we push things, we add things, we do stuff. And in the end, same with this one, with this one. Let's compare 0. What for? So the result is 100. What the hell is going on there? Don't get it. I don't get it. Well, I don't quite know what to do about that. I spend a lot of time looking at the instructions. Maybe it makes sense to kind of look at the lowering to bytecode a bit and see if something jumps out. Yeah. Okay. Compiles an expression, assumes that the stack is already aligned for the expression. So for the padding, we just push padding. For the byte, we push byte. For the int, we push 8 bytes. If this is a local variable, then we actually copy stuff from the stack. The local, and this is the expression size. Sure. Yeah, for an aggregate, we compile the individual fields. For a member, we align the builder to the member of alignment. We compile the member of. Okay. We switch. I don't quite know how that works, but sure. Here we have a call. We have well. No idea. No idea at all. So, there are a couple of things I can take, a couple of paths I can take, but all of them are quite comprehensive and probably worth their own video. The two main things I think I can do is, first of all, optimizing the waffle. At least in the sense that the waffle supports nesting of expressions. For example, in here we have this padding expression directly in this aggregate instead of a separate padding expression before that. I can greatly simplify the waffle, I think, by, for example, saying that this case just immediately returns an empty aggregate instead of first creating a local and then pushing that. Or, for example, for every call in the, was it pudding, pesto, whatever, we first create this struct with the arguments. And then we make the actual call. And before that, we also have to build the arguments. And at the end of the scope, they are no longer used. So rather than creating local variables for each of these, and every local variable reference is actually like a complicated copy from stack thingy, I think it would rather make sense to inline most of these. Basically inline everything that's possible. Yeah, for example, in here, this is an aggregate of this thing, and this is a local reference which copies something from the stack from before. Like we should just put the 4 directly in here, and also remove this padding of 0, and yeah, this is fine. And also not have a local variable for that, and then copying that from the stack to the stack to return that, and then popping below the top some other stuff. We should just return this immediately right here. Yeah, and kind of folding these waffle expressions really makes a difference, I think. Also, like this right here, adding, like this is something with a size 0, size 3, and we get the thing at offset 0 of size 3. Well, we can just remove that. We can just inline that directly in here. So this could just be, you know, $0.2:1. That would be nice. Yeah, so kind of, you know, optimizing the waffle really, like, can really make a difference, because a lot of this, each of these local variables introduces a lot of this stack copying stuff. Every single one, and you can see like there's a lot of stack copying. All these push and pops, you know, push, pop, like everything I see is a push and a push or a pop. Yeah, trimming that down would make a lot of sense. But then again, I'm not sure if that is really, you know, if that just makes this problem in this instance disappear without fixing the underlying problem. Like if it just disappears the problem, then well, we haven't really learned anything of why that problem exists. But if it trims this representation down to something that you can more easily debug, that would be pretty valuable. That's the first part, optimizing the waffle. Second option would be to convert to kind of serialize the bytecode into some sort of file and do a lot more stuff with that, like make that more inspectable, make that more debuggable, maybe even have a separate VM in, you know, a systems programming language, like in Zig or something, that would kind of allow, you know, adding more debug stuff, treating that more as a first class thing. That wouldn't really make a difference, you know, but it would at least force me to have a really like clean layer of separation between, you know, now we're serializing this bytecode. That means that we can't just have these jump instructions with a literal address that we jump to, where we just expect other bytecode instructions to be. Rather than that, we would probably have an index into the list of instructions, you know, something. Yeah, so that would be another kind of boiling this down, this representation, and simplifying that, and kind of having a clean cut there, having a sort of specified binary format. But that would be a lot of effort. It is something that I want to do anyways, same as with the optimizations. But the question is, what is the fastest way to kind of fix these bugs, you know, and kind of make something that is robust. Of course, I could also write tests that would actually be pretty cool. And to that regard, the third most interesting option, I think, is actually writing some code that can execute the waffle, that can kind of look at, you know, that can kind of interpret that by just kind of storing, well, I have these locals in scope, and for each of these it just has some bytes. And these operations here, they should be doable. They should, like, you know, they are quite simple. Yeah, but each of these three approaches requires not just effort, but significant effort. Well, and probably a separate video. Yeah, so I guess even though the code still has bugs, I believe these bugs, like these are bugs in the waffle bytecode layer and not in the layer above. You know, like what we did in this video with the dupe and drop implementation, that looks correct, and that shouldn't really affect the underlying stuff. That there is a bug deeper in the VM, deeper in the code, and I think it's like I should rather focus on fixing that in a separate video and doing, you know, kind of these more effort but more systemic approaches of eradicating such bugs, such as having a separate, you know, kind of spec, just thinking what is the bytecode, defining that, specifying that, having separate implementations in Zig that also track allocations. Like I know Zig has some nice features that alert you if some allocation is not freed, you know. So this would be really nice for debugging the memory safety of the code, the generated code. And also it would be more performant probably, and in general I think worth doing. Yeah. Anyways, testing would make sense, definitely. But I'd rather, actually I'm more a fan of these kind of end-to-end tests. And maybe also testing from the bottom up, like testing just the bytecode. Testing just, you know, are these instructions working as I expect? And then working my way up, you know, having some waffle stuff and seeing if that returns the correct thing. Yeah. And in general, like, I am a fan of end-to-end tests, just having a string that represents a program, having the output of that maybe, or even a separate, yeah, maybe the output, something like that. Yeah, I think to make Plum more robust, it makes sense to go from work my way up from the bottom of the stack. So that's probably going to be the next video. But for today, that's it. Bye.